The information in this module is accurate and complete to the best of our knowledge. All recommendations are made without guarantee on the part of the author or the sponsoring institutions. The author and the sponsoring institutions disclaim any liability in connection with the use of this information.
In this module, we discuss a variant of Needleman-Wunsch pairwise sequence alignment algorithm for solving the semi-global alignment problem. Describe the main changes in the Needleman and Wunsch algorithm that allowed the computation of semi-global alignments. Explain why these changes produce a result that is consistent with the abstract notion of semi-global alignment. Explain why the computing time is essentially the same as in global alignments. This is a definition on semi-global alignment that was introduced in the module on alignment problems. In that module, we noticed that the definition is rather intuitive. In this module, we discussed algorithms which, as many instances in bioinformatics, that implement an interpretation of this definition and thus provide a well-defined meaning to the intuitive notion of pattern. The essence of the idea of keeping Y as a pattern was depicted as confining the alignment to a small box not much wider than the length of the smallest sequence. In the most common version of semi-global alignment, the Needleman-Wunsch recursive relation is kept as in the original global alignment algorithm. The border of the dynamic programming array D is, however, initialized with zeros. In this way, the gap insertions that are before and after the alignment box are assigned a cost of 0 and thus have no weight in the alignment score. Also, the score is not longer the value in D, NM, as in global alignments, but the value of the maximum entry in the last row of D. This is due to the fact that sequence Y is fully aligned with a prefix of X each time the recursion reaches the last row of D. Consistently, the trackback process starts at the position where this maximum occurs. As a way of illustration, we find the semi-global alignment of these two amino acid sequences using the scoring scheme consisting of the Blossom 50 substitution matrix and a linear penalty gap map with a gap open penalty of 5. As remarked before applying the Needleman-Wunsch recursion, the matrix D is initialized with zeros in its borders. And this is the array D that results from the recursive application of the Needleman-Wunsch formula after the initialization of its borders with 0. By direct inspection, we see that the maximum value of an entry in the last row is 24. Thus, the score of the semi-global alignment is 24. The 6x6 character blue box is the minimal possible alignment box. A semi-global alignment will fit within this box if it's either a perfect match or a combination of matches and mismatches. If the semi-global alignment includes gap insertions, it will extend beyond the borders of the blue box. Thus, the closer is the semi-global alignment to fit within this box, the better the alignment. The semi-global alignment constructed by backtracking the Needleman-Wunsch recursion from the position in the bottom row that holds the maximal entry consists of 5 matches and 3 gap insertions. The semi-global alignment produced by the backtrack process fits within the optimal alignment box except by 1 character. In addition to initializing the border with zeros and starting the backtrack process from the position of the maximum value in the last row of D, some global alignment implementations do not insert gaps in the largest sequence. This is recommended whenever the largest sequence is to be treated as a reference sequence and thus cannot be modified. We compute the semi-global alignment of the previous sequences using the same scoring scheme, but this time without gap insertions in X. This is the array D computed now without gap insertions in X. As expected, the maximum value of the entries in the last row, this is the score, is lower than that of the semi-global alignment with gap insertions in X, since the latter has one more option to improve the maximum. This time, the backtrack process returns one gap insertion and two mismatches, which are highlighted in yellow. In some circumstances, multiple entries of the last row of the array score of the semi-global alignment hold the maximum value of the row. This is the case, for instance, of the sequence X and Y in this slide. The array for the alignment of these sequences yields a maximum of 15, which appears in position 4,7 and 4,8. Each maximum is the origin of a separate traceback process. These are the two semi-global alignments that result from the backtrace processes and be programmed for returning all possible semi-global alignments. The default alignment is the one that starts in the position of the first maximum from left to right. In cases where the entries with the maximum are close together, the choice of the first maximum from left to right ensures that the semi-global alignment fits within a smaller alignment box, as shown in this example. It turns out that the computational time and the memory space requirements of the previously discussed semi-global alignment methods are not significantly different than those of the global alignment. The core producer, which is the computation of D, with repeated applications of the Needleman-Wunsch recursive formula, is the same for global and semi-global alignment algorithms. And although backtrack in semi-global alignment is on average shorter than the one performed in global alignments, the weight of this process is the whole computation in minimal, as it involves far less operations than the computation of D and requires minimal storage space. Thus, if the computing time required by a semi-global alignment is still proportional to the time required to compute the Needleman-Wunsch recursion, we have examined in some detail two simple adaptations of the Needleman-Wunsch algorithm for finding optimal semi-global alignments. These adaptations make feasible a computation that is unfeasible by direct search to the cost of carrying over the same time and memory space cost of a global alignment.